Welcome you all. Welcome to my next lecture. Now, in my last lecture, I talked about or introduced the notions of analytic functions and couple of results concerning analytic function I was discussing. So now today my plan is to just complete that couple of results of analytic functions. Of course, there are many results, but I'll maybe just explain one or two, and then I'll introduce the notions of what is called harmonic functions. Then you will see there is a connection between analytic functions and harmonic functions. Then I'll explain how to calculate harmonic conjugate, and then I'll talk about what is called multivalued functions and its branch. So as I said, I was talking about couple of results regarding analytic functions. Now this is the kind of, I put it as a theorem. So these are the properties. So what is the theorem? So the theorem says that if I have a function f, say, which is of the form u plus iv, which is an analytic function defined on a domain means open connected set, then I am saying that if one of the following conditions true, along with that, then you do not have any other choice unless your function has to be constant. Okay, so if you remember, I have already explained that if the derivative is 0, so then your function has to be constant. So basically you have to play with Cauchy-Riemann equation, that's it. And if you just play with Cauchy-Riemann equations or necessary and sufficient conditions for differentiability, you are done. So these are the things I have done. 1, 2, 3, 4, all things done. 5 also done. 6 is the one. There you need little bit of algebra, algebra you need it. Apart from that, earlier one kind of just back and forth argument. Okay. So that is one, and then 8 also I have discussed. So the only things remaining 7 and 9. Maybe just let's see 9, the point 9. Okay, so what is 9? 9 says that, okay, so you have a function f which is u plus iv, which is an analytic function in a domain. Along with that, I demand that my mod of f, this is also an analytic function. Then I have to show that f has to be constant. There also you can easily how to approach, or you can guess it. See, what is your hypothesis? Hypothesis that f is analytic, it is given, perfectly all right. So now it is also given that f of z is also analytic. Now f of z is analytic means what? Now it's defined g of z, which is modulus of f of z, right? Now this is analytic, it is given, is analytic, it is given, right? Now what is this? That means g is an analytic function, but what is modulus of f? Now if f of z is a complex number, now modulus means what? It is a what? Real number, positive real number. So therefore g is an analytic function, and what about the values of g? It is taking real value, or in fact positive real value. So therefore, with the hypothesis that modulus of f is an analytic function, that means the function g of z, which is nothing but modulus of fz, which is an analytic function, and it is taking purely real value. Now come back to here. Look, if I have an analytic function which is taking purely real value, then what you have concluded? That function has to be constant. So that means g is constant, k1. G is constant means what? Modulus of fz is constant, right? Now modulus of fz is constant, look, come, go to 6. Modulus f is constant implies f is constant. So this will implies f is constant. Okay. So very kind of, you have to use the earlier one as well, right? So that is one. So if modulus of f is constant, along with the fact that f is analytic functions in a domain, then your f has to be constant. So you do not have any other choice. So only the kind of results remaining is a 7. What is 7? 7 is that if I have an analytic functions with the fact that principal argument is constant. Now assume that principal argument, so assume that argument of fz, say let it be theta, and this is true for all z in D, right? But now what is your fz? F of z, which is nothing but modulus of fz times e to the power I. Okay, so maybe I'll just now this is done, right? So I'm just removing this part, maybe do it here, okay? Okay, so now do. So what is that? So it is given. So argument, principal argument of fz, which is constant, let it be theta for all z in D, right? Now any complex number has a polar form. So therefore f of z I can write modulus of fz times r e to the I theta, I of principal argument of f of z, right? What is that? This is modulus of fz, this is e to the I theta, and theta is constant, and this is true for all z. Correct? So now this is okay. So therefore now you can have it. So what it will imply? This will imply that fz times e to the power minus I theta, which is modulus of fz, and this is true for all z in D. Now f is analytic given. This is what? This is some constant. So constant times analytic function, that is also analytic functions. So therefore what it will imply is that modulus of fz, this is an analytic functions, right? Because modulus of fz, which is f times e to the power minus I theta, where e to the power minus I theta is constant, because argument of fz is theta for all z. So therefore left hand side is an analytic functions, and this is exactly equal to modulus of fz for all z. So what will imply is that z goes to modulus of fz, which is an analytic functions. But just now I have discussed in 9, if this is an analytic functions and this analytic functions, it is taking purely real valued, what will implies? This will implies that modulus of f, so just the earlier one is using the 9, z goes to modulus of fz. If it is an analytic functions, that means it is an analytic functions taking purely real valued. So this will implies that f is constant. Okay. So therefore actually I am using the earlier one to conclude the next problems. Okay, so these are very basic results of analyticity. So that means, so fundamental is that 1 to maybe 5 you can think about it is fundamental. 6, 7, 8, 9 you can prove using 1 to 5. And to prove 1 to 5, what I have used? I have just used that f is an analytic functions. That means my function is differentiable. Necessary conditions implies that it is satisfying Cauchy-Riemann equations. That's it. And of course you have to say that since it is a satisfying Cauchy-Riemann equations, then that means you are like transforming your problem to U and V. U is a map from R to R and V is a map from R to R. In fact, some domain, nice domain, open connected set from R to R, where all the partial derivatives of U and V vanishes, and then using the results of real analysis, you can say that U is free from X and Y, V is free from X and Y. So therefore U is constant, V is constant, and F is constant. So these are the couple of problems. If you solve, then you have some understanding or some like experience that how to handle that Cauchy-Riemann equations, or how to solve some problem using Cauchy-Riemann equation. This is very few. There are many. If you kind of look for some books, some problems, maybe these are the techniques might be needed to solve those problems. Okay, these are very few I am saying. This is not the kind of complete list. There are many problems, but these are the fundamental problem. One should look for that. One should try for that. Okay, so I have discussed all 1 to 9. Okay. In fact, you can expect in your exam this sort of problems with some twist will be there. Okay, so just you have to use cleverly the Cauchy-Riemann equation. That's it. Yeah. So now next my target is to talk about harmonic functions. So now you may ask, sir, why harmonic functions? We are kind of discussing with analytic functions. Why harmonic function came into the picture suddenly? Later you will see there is a connections with the analytic functions and the harmonic function. And what is that? If I have analytic functions and if I write my functions f of the form u plus iv, then the real part of f, which is nothing but u, and the imaginary part of f, which is nothing but v, they turns out to be harmonic functions. So before that I need to discuss what is harmonic functions. Okay, so harmonic functions, then before that you need to know what is Laplace equations. What is Laplace equations? It says that let phi be a real valued functions of two real variables x and y. The partial differential equation, so this is a partial differential equation. So that means what? That means this is del 2 phi del x square at the point xy plus del 2 phi del y square at the point xy. Or that is the same notations, right? This simply that phi xs y plus phi yy. So this Laplace equations, this is, that means the, what is this? This is second order partial derivatives of phi with respect to x variable. This is second order partial derivative of phi with respect to y variable. So if del 2 phi del x square at the point xy plus del 2 phi del y square at the point xy is equal to 0, or phi xx xy plus phi yy xy is 0, then this differential equation is known as what is called Laplace equations. Sometimes it is also known as what is called potential equations. Now what is the definition of harmonic functions? Harmonic function says that you start with a real valued functions phi, say from R to R, or some domain subset of R to R, is said to be harmonic. As I said, is in a domain. So therefore phi is a map from maybe D subset of R to R. What are the conditions it should satisfy? So you start with a real valued functions phi from some domain D subset of R to R if all its second order partial derivatives are continuous. So that means what? That means del 2 phi del x square del 2 phi del y square, and mixed will be there, del 2 phi del x del y or del 2 phi del y del x. Okay, so that means all second order partial derivatives should exist and they are continuous. Not only that, it should satisfy Laplace equations. That means at each point of D, my phi should satisfy the Laplace equation. That means it should to phi xx xy plus phi yy xy should be 0. If a function phi satisfies all those properties, that functions I am saying it is an harmonic functions. Okay, so harmonic function means it should be a functions from some nice domain D subset of R to R. I'll say that my function phi is harmonic if all second order partial derivatives should exist and they are continuous. Not only that, it should satisfy what is called Laplace equations. If a function phi satisfies all those properties in a domain D, then I will say that my function phi is an harmonic functions. One simple example you can take. So phi of xy, just simple take x, if I just say. Okay, because what is that? Because it's a nice functions, right? All the second order partial derivative exists. And what is the second order partial derivative? Phi xx is 0, phi yy is 0, phi xy, that is also 0, is equal to phi yx. Okay, and phi xx at the point xy plus phi yy at the point xy, that is also 0. So therefore this is a very nice function. So therefore these functions, all the second order partial derivative exists, they are continuous and it satisfies what is called Laplace equation. So therefore it is an harmonic functions. Okay. Now then I just explain why I need harmonic functions, because there is a connection with the analytic functions. And what is that? This is the theorem. Real and imaginary part of analytic functions are actually harmonic functions. So what is the statement of the theorem? So if f is of the form u plus iv, which is analytic functions in a domain D, then each of the functions u and v are harmonic. Okay. And of course one can prove that theorem. Why? Because you see, what I assume is that f is u plus iv and it is an analytic function, right? So that's my assumptions. Now once this is an analytic functions, so therefore what is the necessary conditions for analyticity? The real part of f and imaginary part of f, that means u and v, they should satisfy Cauchy-Riemann equations on the full domain. That means it will implies, analyticity will implies ux is equal to vy and uy is equal to minus vx, right? Okay, so that's the first definition of analyticity. Then my demand is that u and v harmonic. So now to prove that u and v harmonic, what you have to check? You have to check that all the second order partial derivatives of u should exist, right? And it should satisfy what is called Laplace equations. Now I have a functions u which is a map from say some domain subset of R to R, right? And analyticity implies my first order partial derivative exists of u and it should satisfy these equations, right? But you see, to talk about harmonicity, I need the second order partial derivatives. But if you remember, there is a theorem I have like just stated, but I didn't prove it, that if my f is analytic, then all order derivatives should exist, right? That means f prime should exist and they are also analytic. And this is a very strong theorem because analyticity is a very rigid property. Right. So if f is analytic in a domain, then all order derivative exists and there also should be analytic. So I didn't prove that one. I said that when I will talk about what is called Cauchy's integral formula, during that time I will explain that part, or when I will talk about what is called, I will introduce the notion of what is called power series or Lorentz series. This kind of, when I will talk about the, or maybe at the power series expansions for analytic functions, there I will talk about that, yes, if my functions f is analytic, then all order derivative of f should exist and they are also analytic. But if I assume that fact, now f is analytic given, so therefore f prime is also analytic, right? Now f prime means what? How this is ux plus I vx, this is the expression if you remember, right? Or in terms of x variable, or this is also ui plus I minus I times vy, that is also fine. So now if f prime, since f is analytic, so it is one time differentiable, it is two times differentiable, it is n times differentiable for any n, and not only that, all the derivatives should also analytic. That means f prime is also analytic. Now if f prime is analytic, that means it should satisfy its real part and imaginary part should satisfy what is called Cauchy-Riemann equations. Now what is the real part? Real part of f prime, that is ux, and what is the imaginary part? Vx. Now what is the derivative of ux and vx? First order partial derivatives. That means I am talking about the second order partial derivatives of u and v. So to talk about the second order partial derivative of u and v, you need to go to from f to f prime, and there you need to take the derivative, first order partial derivative of your ux, vx, u and vy, and it will give you the second order partial derivatives of u and v. And I can do that because if f is analytic, then f prime is also analytic, f double prime is also analytic. So therefore all order partial derivatives of u and v there exist and they are continuous. So that is one of the kind of observations you should remember, provided you assume that the statement of the theorem is true. That means if f is analytic, then it's all order derivative of f that exist and they are also analytic. If I assume that one, then analyticity of f implies all order partial derivatives of u with respect to variable x and y exist. In particular, second order partial derivatives, they exist and they are continuous, right? That is okay. The only thing is remaining to check that whether it will satisfy your Laplace equations or not, and that is also okay. Why? Because analyticity implies not only the partial derivatives of u and v exist of all orders, but also it should satisfy Cauchy-Riemann equations. If I have this one, then look, if I calculate, so this is the equation, so if I take the partial derivative with respect to one x variable, once again, then uxx, it should be vxy, right? That means first, or you can say that this is del 2 del x of vy, right? And what about this one, uyy, that means this should be del y of minus vx, right? And what is that? So that means this is actually, that means this is the, I am taking the partial derivative with respect to x variable of vy. So that means you can say, right, this is del to v. So first this is del x del y. So that means first I am taking the partial derivative of v with respect to y variable and then x variable. And what is that? This is minus will come out because as a constant. So therefore this is del to v, then this is del y del x. So that means first I am considering the partial derivative of v with respect to x variable and then y variable. So if I add it, that means uxx plus uyy, what is that? That means del to v del x del y minus del to v del y del x. But then what I need to check that whether this is 0 or not. But this is 0. Why? Because again, you see again the theorem of real analysis in the multivariable calculus. If I have a nice functions and if your all second order partial derivatives there exist and they are continuous, then your mixed partial derivatives, they are same. So that means it doesn't matter which order I am doing the partial derivatives. That means first I am taking the partial derivative with respect to y variable and then x, or first x then y, both are same. So therefore in other words, del to v del x del y, which is same as del to v del y del x. So if all the partial derivative exists and they are continuous, there is a theorem in multivariable calculus. It says that all the mixed partial derivatives should exist and they are equal. But I have a function f is analytic, so all other derivative of f exist and they are also analytic. So therefore your partial derivatives of u and v, whether all order partial derivatives, they exist and they are continuous. So therefore it will have this kind of properties, which will implies that uxx plus uyy is 0. So therefore u satisfies Laplace equations. Along with that, all the second order partial derivatives of u exist and continuous. So therefore u is an harmonic functions. And similarly you can say that v is also harmonic functions. So this is very nice. So therefore if I have analytic functions which is of the form u plus iv in some domain, nice domain, then it implies that its real and imaginary part are harmonic functions. Okay, these are the examples I have given. The functions x square minus y square 2xy e to the power x cosine y e to the power x sine y. These are all harmonic functions in C. Now the functions ux is equal to log of x square plus y square to the power half. This is also harmonic functions in the, not on the whole complex planes, but if I take out the origin from the complex plane, it means punctured complex plane, this is an harmonic functions. But you just check, it's very easy, you can check it that these are the functions harmonic. For example, x square minus y square. So what is the first, you just say that, okay, this my function is say f of xy, which is x square minus y square. I have to check that this is a harmonic functions or not. What you have to check? You have to check all the second order partial derivatives should exist and continuous, but this function is nice function. It is a polynomial in x and y, so therefore all other partial derivative exists and continuous. So in particular, second order partial derivative exists and continuous, and just you have to check whether this is true, fxx plus fyy, that is 0 or not. But if I calculate the fxx, what it will give for the expression? So fx it will give 2x, and what is fxx? It will give you 2. And what is fy? Minus 2y. And what is fyy? Minus 2. So therefore fxx plus fyy, it should be 2 minus 2 is equal to 0. So therefore this function's f of xy, which is x square minus y square, second order partial derivative exists and they satisfy Laplace equation, so therefore it is harmonic functions. Similarly, I am just leaving it as an exercise. 2xy, these are the functions. These are all nice functions. In fact, these are polynomial in xy, or is a combination between trigonometric functions and exponential functions. These are all nice functions. All order partial derivative exists and continuous. So only thing you need to check whether it will satisfy your Laplace equations or not. You just check it, it satisfies Laplace equation. So therefore you are done. This is another one. It is apart from this involves log functions, but even then these functions you can check. This is a harmonic functions, what is called in a punctured complex plane. Okay, let's take it as an exercise and do that. Okay, now come to the what is called the notions of harmonic conjugate. What is harmonic conjugate functions? Look at the definitions very carefully. It says that you start with the harmonic function. So let u be harmonic functions in your domain D. Now, if there exists another harmonic functions, if there exist harmonic functions v in a domain D such that u plus iv, it will be an analytic functions. It is analytic in D. Then I am saying that my functions v, which is nothing but the imaginary part of the analytic function, it is a harmonic conjugate of u, which is the real part of f. So definition is clear. So what is harmonic conjugate? So you start with the harmonic function first, u. Then I am saying that if I start with the harmonic functions, if I get another harmonic functions v such that u plus iv, if I calculate that one and if it turns out to be an analytic functions, then I am saying that my functions v, which is an harmonic conjugate of u. It is very important which order they are appearing. So that means I am starting with the harmonic functions u, then I am giving an existence of another harmonic, if it is possible. If there is another harmonic functions v such that u plus iv is an analytic functions, then I am saying that my functions v, which is an harmonic conjugate of u. But I am not kind of flipping u and v. I am saying that starting with u, if there is a harmonic functions v such that u plus iv, this position is very important. First u plus I times v. If this is an analytic function, then I am saying that v is a harmonic conjugate of u. Okay, so that's why I have written a note. Please see, in the definitions of harmonic conjugate, note that it is not said u is a harmonic conjugate of v. Rather, I am saying that v is a harmonic conjugate of u. Or maybe you can say that u has a harmonic conjugate. Okay, so that's how you can think. So therefore start with harmonic functions u. If there exists another harmonic function v such that u plus iv is analytic, then I am saying that v is a harmonic conjugate of u. So therefore this note, it should be very careful, because if later on I will see if u is a harmonic function and suppose u has a harmonic conjugate, say let it be v, that means u plus iv is analytic. Using that you can conclude that if v is a harmonic conjugate of u, then minus of u is a harmonic conjugate of v, and that is very trivial, because if v is a harmonic conjugate of u, that means what? U plus iv, let it be f, this is analytic functions, right? So now what will happen if I hit it by minus if? Then what it will give? So that means it will give you v plus I times minus u, right? Now if f is analytic, minus I times f, that is also analytic functions, because I am hitting f by some constant. Now look in the right hand side. V is a harmonic functions, then I am having another harmonic functions which is minus u, such that v plus I times minus u, which is an analytic functions. Then what can I say? So that means I will say that minus of u is a harmonic conjugate of v. So therefore if v is a harmonic conjugate of u, then minus of u is a harmonic conjugate of v. So therefore the term I am saying and the position I am taking is very important. So start with the harmonic functions u. If there exists another harmonic functions v such that u plus iv is an analytic functions, then I am saying v is a harmonic conjugate of u. Not u is a harmonic conjugate of v, but v is a harmonic conjugate of u. Suppose v is a harmonic conjugate of a harmonic functions u, then using this conclusion you can say that minus of u is a harmonic conjugate of v. Okay. So this is also this I have examples. So again these functions are harmonic functions. So maybe I will calculate this one. So what will happen if I start with these harmonic functions u xy, which is exactly equal to x square minus y square in C. These are harmonic functions. I just checked my last slides. Then I will show that there is a way to calculate the harmonic conjugate. So starting with the harmonic functions u, what will be your harmonic conjugate? So harmonic conjugate definitions you know. So you have harmonic functions u. If there exist harmonic functions b such that u plus ib is an analytic functions, then that functions b I am saying it is an harmonic conjugate. Now given a harmonic functions, suppose explicit expression of harmonic function is there, then in your exam it will, some problem will be there. I will say that okay, what will be the corresponding harmonic conjugate of your u? Suppose harmonic conjugate exists, then what will be the expressions? So I will prove in my next slides or a couple of slides later that if I start with these harmonic functions u, then there exists a harmonic functions v which is of this kind of form, v of xy is equal to 2xy, of course up to a negative constant, okay, then this function is a harmonic conjugate of your harmonic functions u. Maybe in next slides I will prove that. Okay, before that, sometimes the phrase harmonic conjugate is briefly called also as a conjugate, but you should not confuse with the conjugate of a complex number and conjugate of a harmonic function. So you should be careful. So sometimes the phrase harmonic conjugate is briefly called as conjugate, but it has nothing to do with conjugate z bar of a complex number z. So that conjugate, that means given a complex number z, that z bar, it has nothing to do with the corresponding conjugate of a harmonic functions. So now this is the harmonic conjugate definitions I am giving. Now one can ask, okay, if I have a harmonic functions u, can I always say that harmonic conjugate of that functions u always exist? Answer is no. I will give an examples. For example, this is a functions u which is log x square plus y square to the power half, which is an harmonic functions in a punctured complex plane. But that harmonic functions you cannot have a harmonic conjugate. That means you cannot get a harmonic functions v such that u plus iv is an analytic function. You cannot have it. So therefore, I need to have some kind of conditions on my domain, or somehow some restrictions I need it, so that I can conclude you start with the harmonic functions, then the harmonic conjugate always exists. Now you see, if you just kind of somehow connect yourselves, look, this example says that the functions u defined on full C, and it will have this function, of course, nice polynomial in x and y, and it will have a harmonic conjugate. However, look at these functions uxy, which is log of x square plus y square to the power half, which is a harmonic functions not on C but on the complex punctured plane. But I am saying that the function, it has no harmonic conjugate. Now what is the difference between C? Because earlier one the functions u is defined on C, and here this functions u is defined on C minus 0. So therefore you can guess that the domain is changing. If I change the domain, that means some conclusion is not going in the right directions. So therefore maybe you can think about it has something to do with the domain. But there is a huge difference between the domain C and C minus 0, right? Because there is a punctured. Punctured means what? A topology changes. For example, this C, and you have this domain which is punctured. So major difference is that topologically it is different. For example, this domain C, which is simply connected, but it is not. Punctured complex plane is not simply connected. Now you may ask, what is simply connected domain? Simply connected domain is that if I have a domain, and if I take any simple closed curve or simply closed contour, I can kind of squeeze that contour, or I can make that contour continuously, or I can, what should I say, squeeze that contour to a point without leaving the domain D, or without passing through any singularity. Singularity means, suppose if I squeeze that simple closed contour to a point, and while squeezing, or maybe you can either squeeze, or you can say that I can deform, whatever it is, it's up to you which term you will use. So therefore simply connected domain means if I have a domain, if I take a simple closed contour, and if I deform my contour to a point without leaving my domain D, then this kind of domain you can say that simply connected. So therefore C is simply connected, because if I take this kind of simple closed contour, then I can deform it to a point, like this kind of things, and I cannot exit from the domain, it is always there. However, if I have a domain, suppose there is a origin is not there, and if I take this kind of simple closed contour, then you cannot deform it to a point without leaving the domain, because if I squeeze it or deform it, then at one point of time it should pass to the origin, but origin is not a part of the domain, so you cannot have it. So therefore you cannot squeeze. If I have a punctured complex plane, suppose punctured at the origin, then if I take say circle around the origin, then you cannot squeeze it to a point, and that point, if you can squeeze it, but that point should be an origin, okay? If I take a circle of center at the origin, okay, but therefore, but origin is not a point in the complex plane. So if I take any other simple closed contour around the origin, I cannot deform my contour to a point leaving the domain, without leaving the domain, because at some point of time it should cross your origin, and origin is not a part of the domain. So therefore you cannot do that. So therefore this is a major difference between C and C minus 0. So geometry changes. So therefore one can think about that. So that means if my domain G is very nice, in nice means in that sense, like either it will be full complex plane or say some convex domain or some open unit ball, then that domain is nice in some sense that it is actually simply connected. There if I have a harmonic functions, can I always say that harmonic conjugate exists? Answer is yes. So that's how this existence of harmonic conjugate functions. See, one can raise the following questions. What I am asking, does harmonic conjugate V always exist for a given harmonic functions U in a domain D? In general, answer is no. First example, if I take this functions U, which is a harmonic functions in my punctured complex plane, but it has no harmonic conjugate in G. Maybe I will explain that one. Then I am saying that refining the above questions as follows. What is that? Under what conditions harmonic conjugate V exist? Okay, under what conditions harmonic conjugate V exists for a given harmonic functions U in a domain? Okay, so that means I am giving some sufficient conditions. Can I give some conditions so that I can always talk about, yes, you start with harmonic functions, your harmonic conjugate always exists? The answer to the questions is that yes, there are some domains for which every harmonic functions will have a harmonic conjugate. And what is that? Look, this is the theorem. It says that suppose you start with the domain G. G is either the whole complex plane or some open disk, right? Either full complex plane or some open disk. And if I have a harmonic functions U on that domain G, then U will always have a harmonic conjugate. Then U has a always. That means you can have always a harmonic functions V such that U plus IV is an analytic functions. So therefore, if I start with harmonic functions on some nice domain, that means the full complex plane or open disk, then these harmonic functions will always have a harmonic conjugate. Then I am saying that the above theorem is true if I replace G by simply connected domain, as I said, the simply connected definition of simply connected domain. That means if I take any simple closed contour there and I can deform that contour to a point without leaving the domain. If I have that kind of domain, then if I take a harmonic functions on that domain, then the harmonic conjugate of this harmonic functions always exist. So that is a kind of theorem. I am not proving it, but when I will give a problem, suppose I am saying that okay, check whether harmonic conjugate of this harmonic function will exist or not. Then what will you have to do? First you have to check whether your domain is nice or not. So the problem I will give, by default it is a simply connected domain. So therefore you do not have to worry about the existence of harmonic conjugate. You always assume that yes, that means my domain is nice, either it is the whole complex plane or open disk. That means it is a simply connected domain. So therefore my harmonic conjugate given a harmonic functions always exist. So but I just need some procedure how to calculate the harmonic conjugate, that I will explain. Okay, so for the existence part you do not worry. So if I ask this kind of questions, that check that whether these harmonic functions will have a harmonic conjugate or not, so the existence part you do not worry, because I will give that problem. So the domain is very nice, that means it is simply connected. So next part is that how to calculate harmonic conjugate. Okay, so before I proceed that one, maybe I just explain that why I am kind of so confident that the functions U, which is log of x square plus y square to the power half in this domain C minus 0, it is domain means open connected set, right? So it will have no harmonic conjugate. Because you see, if I assume that there is a harmonic conjugate, suppose your domain is this domain and suppose harmonic conjugate exists, then you will see that your harmonic conjugate will have some precise expression. And what is that? It turns out that if I assume that V is a harmonic conjugate of U, then V is kind of argument functions, argument of Z. Or maybe you can say that principal argument, you can say. So your V is nothing but, V function is nothing but argument functions. But I will prove that argument functions, if I take the Z goes to arg of Z, these functions not even continuous functions in the punctured complex plane. So therefore, if I assume that harmonic conjugate will exist, then your V expression of V will be like argument functions, but argument functions it's not even a continuous functions, because if the functions V exist, then it V what? When I demand that V U and V U plus IV should be analytic functions, right? If it is an analytic functions, then means partial derivatives or derivatives should exist and they are continuous functions. But in the argument functions, which is not even a continuous function, so forget about that next time differentiability or whatever it is. So therefore these functions functions U has no harmonic conjugate, and that part you might might need it. Of course, two things I have to check. First, if I start with u, then I have to somehow convince you that your v is actually argument functions, number one, and then I have to give a justification that the argument functions is not even a continuous function on c minus 0. Okay, so maybe I'll do that one. Before that, instead of showing that the functions u has no harmonic conjugate, let's just calculate that, okay, start with the harmonic functions, which is nice. How to calculate harmonic conjugate? Maybe that will be the better problem, maybe you can start with. Okay, so that's what I am giving like one slides here, that okay, start with the harmonic functions. Maybe this kind of problem, this sort of problem you might kind of expect in your exam. So let u, which is x square minus y square, find the harmonic conjugate, first problem. Second is that further you write your functions f, which is of course u plus ib, and you have expression of u, you have expression of v, and you know z is equal to x plus iy. So I need that functions in terms of z. So this sort of problems you can think about that. So what we have to do, so if I have a given a functions u, and if I say that find the harmonic conjugate, so first things you have to check the given functions I have given you just check where it is defined. So look, this functions u is a map from C to R. So that means or R2 to R. That means it is defined on the full domain C or R2. Okay, that is the first part. And how it is defined? U of xy is equal to x square minus y square. So first you should check that it is an harmonic functions, and then look for the harmonic conjugate. So first you check that it is an harmonic functions. So first of all, these functions is very nice functions, polynomial in xy. So you can calculate partial derivative with respect to x variable, which is that 2x. Partial derivative with respect to y variable, this is minus 2y. And what about the second order partial derivative? This is 2, u yy is minus 2, and u xy is equal to u yx, which is 0, right? So all the second order partial derivative, they exist, they are continuous. Not only that, u xx plus u yy, that is same as 2 minus 2, this is 0. That means u satisfies what? U satisfies Laplace equation. So therefore, your function is very nice functions, all the second order partial derivative exist and they satisfy Laplace equations. So therefore, by the definition that yes, u is a harmonic function. That is the first step. Okay, this first step. Then I have to show, I will show you that okay, so u is a harmonic function, that is the first step. What is your domain? Domain is full C, then C is a nice domain, right? So therefore, by earlier theorem, it will have a harmonic conjugate. And then what will be the expression of B? Maybe in my next lecture I'll explain that, because there will be a problem concerning that. I will give you some harmonic functions and I will ask you calculate the harmonic conjugate. First you have to check, yes, the functions I have given, it is an harmonic function. That means you have to check all the second order partial derivative exists, they are continuous, satisfying Cauchy-Riemann equations, and in the domain is nice, so the harmonic conjugate exists. Then you have to do some process, and if you follow that process, you will have the expression of your harmonic conjugate. And then at the end, you have to write in your functions u plus ib, which is an analytic functions, in terms of z. Maybe in the next lecture, I'll explain how to calculate harmonic conjugate given harmonic functions, provided the existence is there. Okay, I think I should stop here. Thank you.